Okay, students. In the last class, we discussed about the postulates of kinetic theory of gases. So, in the postulate, the very first thing is there is no force of interaction. Means, sorry, first one is the gaseous atom consists of a large number of small particles. They are considered as point masses. And next, they consider there is no force of attraction between those molecules, and the volume of those molecules is negligible. Okay, and next, so the particles which are present in that gases are in a constant or a random motion. They are not fixed at the one position, so they constantly moving with respect to others in a random motion. So while they are in the random motion, they move in all the possible directions. Understand? And next one, so when they are in the motion, random motion, there is a chance of collision. Even though the collision is there, so there is no force of attraction within that molecule, whether the force increases, decreases, like that, the force remains same. So that means what? The collisions are perfectly elastic. Understand? And the next one is, so here as I told you in the last class, okay, for example, 2, 3 particles are there. So each particle has their own kinetic energy. Okay, so if different particles are there, then they have different kinetic energy. That is depend upon what? Speed. If speed is different, kinetic energy is different. Speed is same, kinetic energy is same. But our assumption of kinetic theory is each and every atom should have a different speed, so that means different kinetic energy. These are all the postulates. In that we have to consider two postulates. One is there is no force of attraction between the particles. Next, the volume of the gas is negligible. Okay, so students listen. Here, ideal gas equation is there, that is PV is equal to nRT. Okay, so if we draw a graph with respect to PV versus P, PV is equal to nRT is there, that PV, pressure and volume with respect to different pressure. So that gives a different lines for a different gases. Okay, and first I consider for ideal gas students, it is in a straight manner. Always PV is equal to constant. You know that according to Boyle's law. PV is equal to constant. That means whether the pressure is increases or decreases, for ideal gas, the graph is like this. Understand? For hydrogen, it is like this. For helium, it is like this. For CO2, it is like this. This is what? The graph of a real gases. This one is ideal gas, this one is real gas. Okay, so what is real gas? I will say first. Listen, another one graph is there. If you consider the graph PV is equal to P only, then this is the graph of a ideal gas. This is the graph of a real gas. So there is a difference between the graph of a ideal and a real gas. So this is the experimental data. Okay. So as we know, if the gases are all same, if they follows the PV is equal to nRT form, then there should be a same graph. If it is stable means, constant means each and every term should be constant. But here what happens? They show variable graphs, variation in graphs. What is the reason for that? Here I consider ideal, here I consider real gases. What is meant by real gases? Those are also called as non-ideal. Real gases also called as non-ideal. So first, what is ideal gas? Means which obeys the equation PV is equal to nRT, or which obeys Boyle's law, Charles law as well as Avogadro's law. That is called ideal gas. Real gas means that is called as non-ideal. one which doesn't obey Charles law, Boyle's law, and Avogadro's law, or the one which doesn't satisfy PV is equal to nRT. That is called as non-ideal solution. So real gases are non-ideal gases. So they show different behaviors with respect to PV and nRT. So why I am not taking nRT means one mole of a gas we are considering. R is constant, temperature at a particular temperature. So R remains constant. That's why I consider only PV. This is 1 mole. This is already we know gas constant. Temperature at 25 degrees Celsius or something else. So all the three kept constant. That's why we are only drawing a graph with respect to PV and P. Understand? For ideal gas, PV, it satisfies PV is equal to nRT means it is constant. Understand? Next, real gases, they are not satisfying PV is equal to nRT. That means they are not constant. They have some value. That is what given in this graphs. Okay? So what is the reason for deviation of, this is a deviation from year to year, deviation of real gas from ideal gas. Why the real gas is deviated from ideal gas? Because these two postulates are wrong. Why? So listen, there is no force of attraction between the particles. If we assume that there is no force of attraction, then the gas cannot be liquefied. Okay? You know how the gases are arranged? Like this. Correct? So many gaseous molecules are there, just assume it is like this. If you apply a pressure, then what happens? The volume decreases. Then these atoms are arranged in this manner, means very close to each other. Then what? The gaseous atom become a liquid. When the atoms comes together, then what happens? The gas compresses to what? Liquid. Okay? If there is no force of attraction according to this, then the gas cannot be liquefied. But upon cooling, upon compressing, the gas can be converted into liquid. That means this assumption is wrong. Understand? That means what? The pressure can act in this. So there is a force of attraction in between the atoms and pressure is there. So students here, assume if initially the gaseous atoms are like this, assume this is an ideal gas, that is PV is equal to nRT. Okay? So according to kinetic molecular theory, we are proving this one is wrong by applying external pressure. Okay? So here what happens? The volume decreases from year to year. Correct? That means what happens to the pressure? Increases. Correct? If the pressure of ideal gas is P, if the pressure of this is X, okay? So here it is P, here it is X, means X is equal to P plus some value. Understand? Here pressure is less, here pressure is more. Understand? Okay. Next. So here P ideal you consider, P ideal is equal to P real plus extra correction factor we have to have, because listen, here in the ideal gas they are freely arranged, means there is a force of attraction or a pressure caused by the gaseous atoms on the walls of the container. There is a pressure exerted on the walls of the container if they are far away from each other. Then, if intermolecular force increases, that means assume they are here the molecules are there, too far away from each other. Okay? When they come close to each other, assume this is the gaseous molecules of ideal gas. So in that, they exert pressure on the walls of the container. If the intermolecular force increases, means they become liquid. Then what happens? These atoms stay together, are attracted together like this. Understand? So this shows what? Here I consider another one. Assume this is ideal gas. Okay, they are far away from each other. Intermolecular distance is more. They exert pressures on the walls of the container. Here, the same atoms compress to liquid. Then the intermolecular force increases. Then here pressure is increases here. So intermolecular force between these two increases, means the pressure on this wall decreases. They are moving far away from the pressure wall of the container. Understand? Here they are nearer to the walls of the container. They exert a pressure. When the flow pressure is exerted or when the intermolecular force between them is strong, then what happens? They are far away from the container. Means the pressure is more here. Attraction force is here rather than the repulsion force. Understand? That's why the decreases the pressure on the wall. That means what? In the ideal gas equation, pressure is more compared to real gas. Understand? That's why the ideal gas is equal to the pressure of ideal gas is equal to pressure of real gas plus correction factor. What is this correction factor? But how much we have to add to equal to this ideal gas? Understand? So this becomes P ideal is equal to P real plus A n square by V square, where A is the constant. This is the correction factor. Okay, what is this A, which is very important for 1 marks? Significance of A. A is magnitude of intermolecular force of attraction between molecules or particles. Very important for 1 marks. Okay, what you got here? Here you got for P ideal. So this is the real gas pressure with respect to real gas. Understand? Okay. Next one is second one. The volume of the gases is negligible compared to what? Overall volume occupied by the gas. So students, second one is the volume of the gas is negligible. Means if your container is there, if it is total volume is occupied here, so then volume occupied by the individual particle is negligible, they are telling. Okay, so initially listen, there is no force of attraction between them, means this one is correct because they are far away from each other. We cannot, they are very small, so the individual volume cannot affect on the total volume of the gas. But we proved here what? There is a force of attraction between the molecules. That means what? When they are nearer to each other, they are arranged in a certain manner. That means they exhibit some of the volume. So students, here assume initially this is the volume of a ideal gas. Next, another one you consider, they are arranged in a regular manner as they are liquefied. They are in a ordered manner. So this is the volume of a real gas. Okay, so correction factor we have to add here for volume also. So volume of ideal gas is equal to total volume minus A. Wait. Yeah, B. number of moles into V, because volume of ideal gas is more, this one is less. So we have to subtract it. Understand? V minus NV. This is for what? Volume of our ideal gas is equal to V real minus NV. Understand? Okay. So next, compare the equation PV is equal to nRT. This is what? Ideal gas equation. Then what happens to real gas? At the place of P, what is here? P plus AN square by V square. Correct? At the place of V, what is here? V minus NV is equal to nRT. This is the equation for a real gas. This is the equation for a real gas. Understand? So this is also called as Van der Waals equation. This is also called as Van der Waals equation, which is important for 1 mark. What is Van der Waals equation? And you have to mention the expand the terms. P means pressure, A means this one, magnitude of intermolecular force, Vn means volume, N means number of moles. Okay, V means decrease in the volume or a correction factor with respect to volume. R means rate constant, gas constant, T is temperature. That is 1 mark question. Understand? Van der Waals equation. So that Van der Waals equation is nothing but a real gas equation. Same, it is also equal to PV is equal to nRT. As I told you, the gas one which obeys the PV is equal to nRT, that is for ideal gas. Here also the same formula is there. PV is equal to nRT, but it is not equal to ideal gas. There is a correction factor, either increase in pressure and decrease in volume. You know, pressure increases means obviously volume decreases. Here pressure is more, we are adding extra pressure. So we are subtracting volume. Understand? So this is Van der Waals equation. So according to kinetic molecular theory, the first 2 assumptions are wrong. Okay, that is explained by Van der Waals. That's why this is called as Van der Waals equation. Understand? So the next one is liquidification of a gas. Next one is liquidification of gas. Liquidification means the gases which are converted into what? Liquids. That is called as liquidification. Okay? Wait. So before going to this, I'll explain the difference in the real and ideal gas deviation that is expressed by one factor that is called as compressibility factor. The deviation of real gas from ideal gas is calculated as a compressibility factor represented by Z. Okay, what is Z means? Compressibility factor. It is the ratio of product of pressure and volume to the nRT. Okay, that means this Z is equal to, if Z is equal to 1, then only it becomes PV is equal to nRT. This is ideal gas equation, correct? If Z is equal to 1, then it obeys PV is equal to nRT. Therefore, for ideal gas, the compressibility factor is equal to 1. Okay, next, for real gas. The real gas at low temperature. Okay, at low, so not temperature, at low pressure, Z is approximately equal to 1. Next, at high pressure, Z is greater than 1. At high pressure, Z is greater than 1. In between these, low and high pressure, Z is less than 1. This is called as intermediate pressures. In between low and high. For example, low pressure is 1 bar pressure, high pressure is 3 bar pressure. Okay, so 1 bar pressure is approximately equal to 1. 3 bar pressure is greater than 1. So the 2 bar pressure is less than 1. That is what it is. So these conditions are important. Equation, this condition. For ideal gas, compressibility factor is 1. Compressibility means what? Compress means by applying extra pressure, we have to compress. Understand? That is compressibility factor. Because their pressure increases, volume decreases. Because we are studying, they can liquefy. This is the compressibility factor. This is the values for ideal, real at low pressure, high pressure and intermediate pressure. Okay, that is also important for marks. Now we will study liquidification of gases. First I draw the graph. Graph, just listen. Okay, so students, this part is where the gas is present in a liquid state. Okay, So within this V3, V1, V1, V3 and also pressure up to this behaves as a liquid. Understand? So initially the liquid, when it starts to liquidify means at 30.98 degree Celsius. It is the maximum degree at which the carbon dioxide can be present in a liquid state. So above this it is gas. Below this it is liquid. Understood? So this is the maximum temperature at which it can attain a liquid state. So if it is 30.99, then it is a gas. Understand? If 30.985, then it is a gas. 30.98 is the maximum temperature at which the gas can, the CO2 gas is at a liquid state. So below that temperature it is liquid, above that temperature it is gas. Okay. So students, here I mentioned like VC and PC. What is this VC and PC means? It is critical volume. This is critical pressure, and this one is TC, that is critical temperature. Understand? Why I represent C means at this 30.98 degrees Celsius, it attains some volume and it has some pressure. Okay, that is called critical temperature, critical volume and a critical pressure. Why it is called as critical? So, because it is a very important temperature which exactly decides the difference between gaseous and the liquid state. So, the less continuity between the gaseous and liquid state is called as fluid. Fluid means it is neither a gas nor a liquid. It is just a continuity from gas to liquid or liquid to gas. Okay, so this tells about the fluid character of the gases. Understood? So that means, I'll write first, that is very important for 1 mark. What is critical temperature, critical pressure and critical volume. So the maximum temperature at which a gas is in liquid state called as critical temperature, represented by Tc. Okay, the maximum temperature at which a gas is in liquid state called as critical temperature. What is critical pressure? The pressure at which the gas is in liquid state at maximum temperature. That is called as what? Critical pressure. The pressure at which the gas is in liquid state at maximum temperature. You cannot write the pressure at which the critical temperature, because we don't know what is critical temperature. In the definition you want to write, of course I can say this is the pressure where the critical temperature is there. You cannot write that definition in the examination. The pressure at a critical temperature is called as critical pressure. It is not like that. The pressure at which the gas is in a liquid state at maximum. This tells about what? Critical temperature. Okay, next, for volume also. The volume of a gas at which it is in liquid state at maximum temperature, that is called critical volume. These three definitions are important for 1 mark. What is critical temperature, critical volume and critical pressure. Understood? Okay. So students here, listen. Why we are not considering this one? See, B is there, this one is there. Why we are not considering this one as a critical temperature and pressure? Because here the variation of two molecules are there. Here point 1, 2 is there. Here also 2 is there. From year to year, it remains constant. So listen, here it is a pressure and a volume. Okay, listen. In the x-axis, it is volume. In the y-axis, it is pressure. So at certain pressure, the volume remains constant at certain time and again decreases. Correct? At here, the volume is here. So at this pressure, the volume remains constant at a certain time, then decreases. Okay, next. Here also, the volume remains constant and then decreases. Here, it is not like that. When the temperature increases or the pressure increases, then it liquefies. If the pressure is less, so this cannot tell about the critical pressure. Why? Here, listen, only one point is there. We cannot distinguish from here to here. There is no constant value. At a single point, we can easily say pressure, volume, and temperature. But here, volume is like V1, V2. Understand? So that's why they attain a different volume and it explains about the constant. So the thing is, students, when the pressure is there, volume cannot be constant. Understand? If the pressure increases, then what happens? Volume must and should decreases. Understood? That's why this point is considered as a critical point for temperature, pressure as well as a volume. Because there is no variable is there. It is considered as a single point. Okay? So what is liquidification means? That is what? Conversion of a gaseous molecule into a liquid molecule. The fluid property that is called as liquidification. Gases to liquid. In that we can explain the critical temperature, critical pressure and the critical volume. So what is critical temperature means? The maximum temperature at which the gas can exhibit a liquid state or exist in a liquid state. In the above the temperature, it is a gaseous state. Okay. So the next one is, so this completes the gaseous part. That means, as I told you in states of matter, we are studying regarding gases as well as liquids. So in gases, we studied the characteristics of gases, intermolecular force between the gases, that is van der Waals force, dispersion, dipole, dipole-induced dipole, and hydrogen. Next, we discussed about the different laws: Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law, and ideal gas equation. Okay, based on that, we solved problem also. Okay, and again we study the liquidification of a gas, means how the gas converts into liquid. Now we are going to study about the liquid state of the matter. Okay, so what are the properties of liquid means? Compared to gases, liquids have strong intermolecular forces. Okay? Because in the liquid compared to gas, they are closely arranged. That's true. Listen, here it is a container and this liquid is there. Listen. So from here we can easily say, compared to gases, the intermolecular distance between the molecules is less or more. Intermolecular distance is less. So compared to gases, intermolecular distance is less. If distance is less, then force is more because they are very nearer to each other means the attractive force is more than the repulsive force because they want to be stable. Okay, that's why the attraction force is more than the repulsion force because they are very nearer to each other means for example H2O means it consists of a nucleus as well as electron whether it is in a liquid, gaseous or solid state. Even though hydrogen is there means it consists of one electron and one proton. Oxygen is there, it consists of 8 electron, 8 proton. That means there is a force of attraction. Okay, so that force of attraction is intermolecular force of attraction. Okay, this intermolecular force of attraction is there. So remember one thing, student. If distance is less, force is more. If distance is more, force is less. Okay, next. Another thing. So the liquids, they have mass, volume, and volume, but not shape. They have mass, volume, definite mass they have, definite volume they have, but they didn't have any definite shape. So the shape of the liquid is adjusted as the container it is present. Okay. So students, next one is like gaseous. So these liquids also possess some same type of properties, physical properties. So in that we are going to study. In your chapter you have vapor pressure, Next, in this vapor pressure you have boiling point. Liquid boils to convert to vapor state. For example, water. Water melts means highest melting point is more than 4 degrees Celsius. That means when ice melts, solid melts, it converts into liquids. And liquid boils, it converts into gas. Okay. So next one is surface tension. Next one is surface tension. And last one is viscosity. Last one is viscosity. So listen students, vapor pressure, surface tension and viscosity. That is explained in what? Liquid state. So what is this vapor pressure means? If you boil the liquids, if you increase the temperature of the liquids, they form the vapors. Correct? So those vapors are the gaseous atoms. Those gaseous atoms also exert pressure. You know that. Just now I explained. The gaseous atoms also exert a pressure on the walls of the container. So that pressure is exerted by that vapors is called as a vapor pressure. So in closed liquid what happens? If the pressure increases, what happens to the boiling point? Everything is studied in vapor pressure. And what is the surface tension means? Surface tension means, so listen, if you keep anything on the water, a denser molecule like pin, that pin is slightly denser than water and it is lighter also. Okay, but compared to that water, it is slightly denser atom pin. Okay, so students, if you keep that pin without disturbing the surface of the water, it will float on the water. Understand? If you keep here container is there, here water is there. Okay, if you keep that pin without disturbing the surface of water very slowly, okay, then it floats on the water. It cannot go inside. Okay, if you disturb the surface, then it will go inside. Okay, that is because of surface tension. And what is that surface tension we have to say? So, listen, always if you see Observe the flowing of water drop by drop. Okay. Initially, the drop from the tap like this, and later it is like this in the form of a sphere when it falls. Correct? Initially, while it is at the tap, okay, it is in this shape. Later, it is in this shape. What is the reason of the spherical shape of the drops? That is, we are going to study in this surface stage. Next, viscosity. Viscosity means, so in the slant table or any pad or anything, okay, slant table you are seeing. So in that, if you drop, your slant table is there like this, okay. If you drop water and oil, here the place is anything is there. Here I assume it is a land. Okay. Here this is water. Here this is oil. Which one reaches the land first? Water and oil. Which one reaches the oil first? Water. Because it flows very fast compared to oil. So if oil is there and honey is there, this is oil, this is honey. Okay, which one flows fast means oil will flow fast rather than honey. What is the property of that? Even honey is a liquid, oil is a liquid, water is a liquid. Even though their flow property or the speed of the flow is different, that is called as viscosity. These are explained as these are considered as the physical properties of the liquids, which we are going to study in the next phase. Okay, thank you.